Okay, so let's get started. Before I start, two announcements. First is this Friday is Monday schedule as per the academic calendar. Okay, so there is going to be a class on Friday because it's a Monday. It's actually the next Monday's class is put on this Friday as per the university schedule. I'll send an email about this, but just keep in mind that any class you have on Monday, including this one, there will be a lecture this Friday. Okay, that's the first announcement. And then the second one is about the problem set. I handed out one. Okay, it is due next Tuesday, but there was a lablet due this week. So just to reduce confusion, I extended the deadline of the lablet. So that's also due next Tuesday. Okay, and then there is another lablet due next Friday. So there's nothing due this week. Okay, so the problem set three, the homework and the first lablet are due Tuesday. And then the second lablet in the homework is due the following, that Friday, next Friday. Okay, so just keep this in mind. So we'll get started. I hope you had a good Monday. I gave the class off. Hopefully you got to see the eclipse. Okay, but we have to now resume, and I will have to announce a makeup class because of the missed lecture. We'll do that a bit later. All right. So today we will talk about replication. We looked at this briefly last time when we were talking about consistency. Remember, I was talking about various consistency models. Today we'll actually talk about actual replication protocols. Okay, assuming there's some consistency somewhere in there. How do you replicate content? How do you actually make sure any updates are propagated to multiple nodes and so on? Okay, there are many techniques for replication, and they are slightly different depending on whether we are talking about replication of files in storage systems or file systems, or you're talking about replication of web pages in web servers and things of that sort. Okay, we will come back to web later on. Today's class is going to focus on replication, but largely thinking about either storage systems or things like databases that we have been talking about. So all of this replication is replication of data, number one, and is really looking at how do you do this at a system level, okay, an OS level. Okay? So there will be two parts to the lecture. In the first part, we'll talk about remote write and local write protocol. Okay? In the second part, we'll talk about quorum-based protocol. And then there will be some time at the end, hopefully, for us to start talking about fault tolerance, which is the next chapter for the course and in the textbook. Okay? Let's start with some implementation issues and what do the two types of techniques we are talking about mean. So essentially, we talked about consistency last time. These are techniques that are going to implement those consistency methods, but we actually have to think about how reads and writes are handled and so on. So we'll look at two basic approaches. The first one is called primary based. Okay? In primary based, we'll assume that for every replicated piece of content, let's say it's a file for the purpose of this lecture. For every replicated file, we will assume that there is one primary server that is responsible for handling consistency. And then there are several secondary servers that the primary will then tell them what to do. Okay? So these are called primary based. So in some sense, there's a coordinator, which is the primary. Okay? And these class of protocols will be called primary based. And we'll look at least one or two in the next few slides. And then there is another class of protocols. Those are basically called replicated write. Here, there is going to be no primary. Okay? There's no coordinator. We'll just have a set of servers that are replicating content. It's the client job to figure out which server, which subset of servers to ask for the content, how to perform writes and so on. Okay, so no primaries assume writes can take place at any replica or at multiple replicas. Okay, so we'll look at these two different techniques. We'll start with the primary based techniques, and here we'll look at two types. One is called remote write, the other one is called local write. Okay, in the remote write, essentially we assume that the primary server for your data item is a remote machine. Okay, and we are going to send all of our update requests, read requests, write requests might go to that remote machine that is then responsible for coordinating things. Okay, and we'll look at this through several examples. Okay, here is basically what looks like 4 disks in this picture are essentially 4 machines. Okay. In this particular example, we are going to look at 3 of the 4. We'll come back to the 4th one on the next slide. Okay. There are 3 of these. Okay. We'll assume that the one in the middle is essentially the primary for data item X. This would be file X. Okay. So it's the primary machine responsible for it. So what is going to happen is when clients, which are the boxes shown at the top, make read or write requests, they essentially have to be sent to the primary. There's no replication as of. Okay. So this client makes a read request, R1 comes here, R2 is sent to there, you make a read, the read returns here and comes back. Okay. The write the same way. The write comes to this machine, gets forwarded, and it comes back. Okay, the response. So that's a file server like architecture. Think of it as that node being a file server. All reads and writes are going to the server and coming back with okay. Now this one has no replication, but in the next slide, let's assume that that file now got replicated on all of the machines. Okay. There's a copy of the file on every machine. Okay. This is still the primary, and the other 3 machines are essentially secondary replicas. Okay. They have a copy, but they are not the primary. Okay. So in this case, what is going to happen? In the previous case, when there is no replication, all the reads and write go to the primary. Okay. When there's replication, we'll see that the write goes to the primary and then the primary sends them out, but reads don't have to go to the primary in this case. And we'll see examples of this. Okay. So here is the primary for that file X. Okay. So client makes a write request. It's trying to update the file. That's W1. That's the first step of the write. Okay. And then you will see that that write is just forwarded. W2, the next message goes to the primary saying, here's a write, perform this write. Okay. So the primary now got a write request on the file, is going to perform the write on the file, but then it has to tell all the others saying the file has changed and broadcast the write. So you will see that it performs the write, and then you will see 3 W3 messages, one going to this replica, another going to the second replica, and the third one going to the third replica. So it's essentially send these writes over, and then the writes are performed, and W4 is the acknowledgement saying the write has succeeded. Okay? So writes come to the primary, primary sends them out, gets an acknowledgement. Okay? Simple technique. Okay? So, but the reads are much simpler now because there's a copy of the file on every machine. Reads are local in this case. You will see that this client made a read request. This replica can simply send the read request or the response to that read from the local copy. It does not have to go to the primary because it already has a copy. Is this clear? Yeah, writes go to the primary, then the write is sent to every other machine so that the copies are consistent. Reads can be local in this case. Okay, all right. So this essentially implements sequential consistency. We map it back to what we were talking about last time. It will basically map to the sequential consistency method. Okay, so those are remote writes. There's another class of techniques which are called local write protocols. In the local write protocols, the primary server for a data item keeps changing dynamically depending on where the file is being read or written. Okay, so rather than saying each file has a pre-designated and a static primary, we can say any machine can take over as the primary for any file depending on what is happening in the system, which may reduce the number of messages. Okay, so for example, here's that primary that we had on the previous slide for data item X. If there's a client reading or writing to the data item and it sends all its requests to the other machine first, it may be simpler to just move that primary to that machine. It may just reduce the number of messages. Right? So basically that will reduce the overhead of the messages for reads and writes. But in this case, you will have to now track where the primary has moved because the primary keeps changing. So for every file in the system, you'll have to keep some extra information saying where is that primary because it may not be where the file started off. Okay? So under this scenario, let's look at how reads and writes will be performed. Okay? So here's essentially the same example. That's the old primary here. Okay? Now we assume that this client here sends a write request to the file. Okay? When that happens, the local server essentially becomes the new primary. So it basically says, I'm the new primary. The others are now all secondary. So essentially the write comes here. It's going to send essentially all the write requests to all the other replicas. They'll send acknowledgement. the same kind of technique that we had talked about earlier, except that there's one additional step, that the primary has shifted from the original server to a new server. Okay, so that's basically local write. So writes are always local in this case. Okay, and then we'll see what happens to read. Your question, yes. Okay, that's a good question. We'll talk about that a little bit on the next slide. How do you assume a concurrent write? If there are concurrent writes, then there is no point in moving the primary first, because you can't figure out which machine should have the primary. Then it doesn't really matter. It could still be a remote server. Okay. In fact, when we come back to file systems in about 3 or 4 lectures, we'll come back to this, because we'll see exactly what NFS is going to do. Okay. In that case, what happens is, if there's a single writer, NFS server can tell some other machine to take over as primary. And then if multiple machines or multiple users start writing to the file, it recalls the file, okay, saying that I'm going to take over the role of the primary as I was originally. Now everybody has to send. So it becomes remote write. So NFS can switch between local write and remote write depending on if there's a single writer, you go to local writes model. If there are multiple writers, you go back to the remote write. The server takes back the file. Okay? So that's the short answer. But in this case, there's only one writer. There are multiple writers, then of course you don't move. You just stay where the server is, or the primary is. Okay? All right. So in the replicated write protocol, essentially, just to keep all of this clear, okay, we relax the assumption of one primary. There's no one primary. You will essentially, anyone is allowed to update. Okay, you make synchronous writes to all the replicas. Okay, and you can also do asynchronous, and we'll see what that will do. Okay, but let's talk about the synchronous and asynchronous replication. Okay, so first of all, what do these terms mean? Synchronous replication and asynchronous replication. Synchronous usually means there is some blocking involved. Okay, in synchronous replication or synchronous writes, what is going to happen is, when you perform a write, okay, you are going to wait for that write to be completed at all the replicas before you return back to the application and saying your write has completed. Okay, that's called synchronous. So when you say, let's say you try to write to a file, okay, or you print something to a file, or you write to a file, okay, that call will return only after the write has actually been performed at every single replica, not just your local machine. Okay. Asynchronous replication is the exact opposite, where you can perform the write. It may not have completed at many of the servers. Even if it's completed at one server, you can say, yes, done, and the client can continue. And in the background, the write is going to be propagated to other servers. Okay? There's a difference between synchronous and asynchronous. Synchronous is always blocking. It is safer in that the client knows that every machine now has a copy of that updated file when it actually the write return. In asynchronous, all you know is maybe some machine or your local machine has a copy of the write. The write is still in progress elsewhere, and that write might fail. Okay? Maybe some machine crashes. Okay? So just because the write succeeded at one machine doesn't mean it has completed at all. Right? So that's the fundamental difference. Okay? Synchronous is always going to be slower than asynchronous, because you have to wait for the write to go everywhere, and your write latency will be the latency of the slowest machine in the system. The last one that says I'm done is when you tell the client the write is done. Okay? In asynchronous is much faster, because the write can return after it just performs a write locally on the machine. So the client can continue, but it may so happen that the network might go down or something might crash. So the write never propagates. So then if you reboot the system, you may see an inconsistent state where the write is completed at some machines, not at others, or it may just have completed at one machine and others may not have it, or something like that. And then you might have to delete that write from the system, saying it's inconsistent. Okay? So client might think it's done, but it may actually go away at a later time. Okay? Yes, question. Yeah. So you're saying you can send some additional messages in asynchronous, will that give you the... So the issue really is, you cannot, if you have asynchronous, okay? Let's say the client makes a write, you write to the local disk, and then you return and tell the client saying I'm done. Okay? and then something crashes, and maybe the local machine dies, not something else. So there is no way to notify the client that something has gone wrong, and that is why the local machine can't even propagate the write to all the other machines because it just crashed. Okay? So all kinds of things can happen, but from a client's perspective, client thinks it's done. But at a later time, when you recover, that write might get undone because no other machine received that. Okay? So that might cause inconsistencies. If you tell a process or an application saying, yes, something is done, but then you later on you find that that request was never actually processed by the system, you get inconsistent. Okay? So when you need stronger consistency guarantees, you'll always go for synchronous replication. Okay? So in banking application, database application, you want synchronous because you don't want to perform a transaction. Maybe it's a financial transaction, or maybe you're making a reservation for an airline booking, and maybe the system tells you are done, and later on you find there is no ticket because system crashed or something. You don't want that kind of inconsistency, so you will always do synchronous. Okay? And you will pay for the slowdown because you want better correctness guarantees. Okay? Asynchronous is the opposite. You want fast system to perform better, so your writes will finish faster, but there's always a risk that when there's a failure, something may go wrong. So you are trading off performance for some correctness guarantees because, as I said, in asynchronous replication, there is no guarantee that just because a client is told the write is finished, the write is actually propagated to all the replicas. That may not happen if there is a crash in the system. If the system is working fine, yes, that will happen and everything will be as you expect. But that whenever there are occasional crashes, you might have problems. Okay? With these two pictures in mind, here's a timing diagram of what synchronous replication does. Okay? And you'll see the difference very quickly. So here is a client. Okay? It's saying write 1 to file A. Okay? It's saying set A1. That just means write the word 1 or number 1 to file A. So that's a write. Okay? So that's your essentially this is called the leader, but it's really the primary. Okay? It's going to send all of these writes to all the other replicas. These are the secondary replicas. So you say replicate, replicate, replicate. You wait for all of the acts to come back saying, yes, the write was performed at all of them. Okay? And then you tell the client saying the operation was successful. Okay? So the client is waiting since from the time it sends the write for all of the writes to propagate, for the acts to come back, and for you to be told that it's successful. Okay? That is synchronous. Yes, question. Okay, question during synchronous replication, is read operation blocked? So reads are going to be local. Reads are not blocked. So there is nothing about locking here. I'm just talking about how reads and writes work, as in you're trying to read or write to a file. So when you make a read call, you just go to the local copy and you get a read. In this case, we will see the leaderless protocols. There the reads are done separate in a different way. Okay, there is no locking anywhere in here. The locking has to be performed on top. If there's a database, there's be a transaction manager that will grab the log before doing something. Or maybe some other transaction can't read if there's a write in progress. This is happening at a lower level. So we assume the locks are taken care of. If there's concurrency, you allow that. Okay. So yes, so reads will not block in this case. And in fact, I'll show you an example on the next slide where there is a read and write concurrently, and we'll see what happens. Okay. So here's asynchronous replication. Okay. So what happens here is you will set A is 1. You send the 3 replication requests. 2 of them have returned back. Okay. And you might say it's done. Because in this case, you might say, I just wait for a majority or something like that. You don't even have to wait for a majority. You can just say, as soon as the first write returns, I can just say I'm done. But in this particular technique, you wait for 2 out of the 3 to have said yes, and then you say it's done, and then you will basically, in this case, if you get a read, as was the question was asked, if you say get the value of A, it goes to the third one that is not yet actually acknowledged, you will basically get a thing saying either that key is not found or the file is not found or something like that. Okay? Because so you have a case where the system says write is done, you send a read request, the read request just happens to go to one of the replicas where the write is still in progress, and you might get an inconsistency. That's those kinds of things can happen. Yes, question. Okay, question is, can you do asynchronous replication or asynchronous writes where you don't wait for any of the operations to be successful? You can do that too. Okay, You can just wait for the OS to have received your write request, and then you can simply return. In this case, all you know is the system received your request. That request hasn't even been performed on any of the replicas. Okay? That's one notion of asynchronous. You can say I wait for at least one of the replicas to tell me it's done before I return. Here I wait for a majority, but not all. Various degrees of asynchrony, right? But yes, you could have done that too. You could have just said, as soon as I get the leader receives the request, I said, fine, I got the request. Then everything is done in the background. Okay? In this case, you may actually have known none of the replicas may have even received the write and system made. Okay? Is this clear? Okay, so there's another example we'll get to it in a little bit later. Okay? So those are all primary based protocol. There's still a leader, a primary, or a coordinator. Okay? You can say, what if we make it completely decentralized? There is no leader anywhere in the system. There's a bunch of servers that all have a replica, okay? But there's no leader. If there's no leader, it's the client or the application's job to contact all the servers and perform the reads or write, because there's no one else to tell one another. Okay? So what happens in this leaderless protocol, there's no primary, then consistency is going to be harder to achieve. We are going to use the notion of voting in this case to figure out what the contents of a read or the write should be. Okay? And we'll see an example where how this is performed. So we'll call this essentially quorum-based protocols. So we'll assume that a file is replicated on n servers, okay? And we'll set some rules on how reads and writes are to be performed. Okay? We'll say that you have to pre-select what is called a read quorum and a write quorum. A read quorum says that's the number of servers the client has to contact to ask for a file. And then you have to get that file, and the file has to match at all of those servers for you to actually get a successful read or a write. Okay? So essentially, when you have a quorum, that means reads and writes are performed to groups of servers, not a single server. That quorum is the group. And then when you perform a read, okay, you have to basically read from that group, and so you'll get multiple copies of the file. They have to all match. If they don't match, then the read fails, and then you repeat until you find a matching group where all the servers agree that this is the file. Okay? Think of this as every file is versioned. Okay? Every time you update a file, the version number increases. Okay? So when I perform a read, I get a file with a version number. And if the version number doesn't match, that means some machines have a newer version, some have older. So if a read has failed, I can only return to the client when the version numbers match. Okay? And we are going to guarantee that when the version number match, it is going to be the latest version. Okay? Because we'll set the rules in a way where you can never get a match when or you will never return when the version numbers don't match. Okay? Or if they match, you will always know it's the most recent. So how do you do this? This is basically the rules we'll use. Okay? So NR is the read quorum. That's the number of servers you have to perform the read on. Okay? NW is the write quorum. That's the number of servers you have to perform the write. Write is the same thing. Okay? When you want to update this file, you send it to NW servers, and they all have to perform. Okay? And so the way we'll set the rules is you have to pick NR and NW such that the sum of the two is greater than N. Okay? And then the write quorum is strictly greater than half. Okay? You always have to perform write on a majority. That's the rules we'll follow. Okay? And then read can be chosen any way such that NR plus NW greater than N. Okay? And here are here's what you do. To update, you contact NW servers and get them to agree on the update, which means that you perform the update. For to read, you contact NR servers, you obtain the version number. They all agree, we are done. Okay? And I'm going to show you 3 examples on how this works, so then it's really clear what's going on. Okay? By the way, this is called Gifford's quorum-based protocol. It's a replicated protocol, as we'll see. So there are 12 servers, A through L. Okay? 3 different examples. Okay? In the first example, we set NR to be 3. That means anytime a client wants to read, it has to send the read request to 3 random servers. It can pick any servers at random. There have to be 3 servers. You ask them for the file. They'll return the file. You check the version number. If the version number matches, you tell the client this is the file that you're trying to read. The version number doesn't match. You basically find 3 other random servers and you repeat until you get a match. Okay? And when you want to perform a write, you say pick 10 servers out of the 12 at random and you perform the write. And then those 10 servers now have the most recent version. That's the rule. Okay. So let's take an example here. So the dotted line has 10 servers. That's your write quorum. That's the file. Those are the files. Oh, sorry. Those are the servers to which the file was written to. Okay. So essentially left out A and B, and then C through L got the version. Okay. Now another client is trying to read. It picked A, B, and C as its read quorum. Okay. So A and B will return some older version of the file because they were not part of the previous write. And C is going to return the most recent version. Those version numbers won't match. Okay. So this write is going to fail. Okay. Then you will repeat, and hopefully at some point you will pick 3 random servers from the one that was actually returned to. And then when the file returns, those version numbers will match, and then you will get back a copy of the file. Okay. Now, so I assume you understand what I just said, right? So you can see there is no way to pick 3 files where you can get an old version of the file. So the way we have picked the read quorum, one of those servers has to be in the write quorum, because that's how we pick 3. Because the only way I can do this, if I can pick A and B, the third server has to be part of it. It will not match what A and B have. So I can never get an old version of the file. Okay? There's no way to pick 3 servers at random in this case, where all 3 servers are the old version. They have not seen it. So the reads will always either keep failing until you succeed, and when they succeed, you are guaranteed I got the most recent version. Is that clear? Okay. So here's example 1. Okay. Here's another example. We set the read quorum to be 7. The write quorum is 6 in this case. Okay. The dotted lines are essentially the files that were written to, and the solid ones are the where you're trying to read from. So essentially D, H, L, K, L, I is where you have written this file. Okay. And now I'm picking 7 servers. Okay. So here you'll pick A, B, C, E, F, G. Those are the ones that did not see the file, but you still pick one from that write quorum, so that read will fail. Okay. Now in this case, no matter how you try to read the file, the read will never succeed, because there is no way to pick 7 servers, okay, where all of them have seen the write, because the write quorum is 6. Okay, you're writing only to 6 servers. So when you pick 7 servers, even if you pick all those 6, you will end up picking 1 extra server, and the write will always. Okay. So in this case, you essentially have a case where you are never going to return an old version of the file. That is guaranteed. But you will also never actually complete a write, because the write keeps failing. There is no way to actually make the write succeed, because you pick the read quorum to be 7. Okay. The first thing is, why did this happen? Okay. This happened because we didn't follow our rules. Okay, because we said the write quorum has to be strictly greater than half. Okay, we picked it to be 6. Okay, that's not strictly greater than half of 12 servers. So we didn't follow our own rules, which is why the system doesn't actually work. But we did ensure that NR plus NW is greater than N, which makes sure that you don't actually get bad results from the system, but you're not getting any read results either. Okay. So of course, this basically, the reason this system doesn't work is we didn't follow our own rules. So we're still not doing any bad things. We're not doing any good things either. Okay. Here's a third scenario. Okay. Here, the write quorum is the entire set. NW is 12. So every write goes to all the servers. Okay. And in this case, the read quorum can be 1. It can be greater than 1. It can be 1 because every server has seen the write. All the reads only have to go to a local server. It always succeeds. So in this case, reads will always succeed because you pick the read quorum to be 1. There's no one to disagree with, because you're only asking one server. Okay? But if you're only asking one server, you better make sure that server actually has the most recent file, which is why the write quorum has to be the entire set. Okay? So the write quorum is 12, which is greater than half. Okay? NR plus NW is greater than 12, so we meet our requirements. Okay? And so this is making reads very efficient. Okay. Reads don't have to go to multiple servers. Writes are the least efficient because they always go to others. Okay. This is also called read once, write all. You write to all, and then you read from the local. Okay. So 3 different scenarios. Okay. So if you pick something like this, you will have to perform reads and writes on multiple machines. Okay. And then, as I said, reads might take a while before they finish, because you have to pick 3 random servers that are part of the most recent write group. Only then your read will succeed. But you set the read quorum in a way that you can never get bad results from the system either. Okay, yes, question. Question is, if we have the version number anyway, why can't you return the file that has the version? That's your question, right? So this is a voting-based protocol. So you want to actually make sure all the files match at multiple replicas. Okay? Because you don't know sometimes whether what to know, what to trust or what not to trust. I mean, in some sense, you may not actually need to keep the version number also. Okay? You might just have file contents. Okay? Version number is a simplification I added to the protocol. So it's easier to understand. Just assume I'm getting files with some content. Okay? You can just do the diff on the file. If the files match, I say that's the right one and I return. The files don't match, I repeat. This protocol will work in that case either. You are right in that if you add the version number, that's giving us extra information. Maybe you can simplify this further. But the protocol itself doesn't actually need actual version number. It just needs the content to match. Okay, so that you can do without keeping any version. The version number makes the protocol easier to understand. Okay, but you are right. I mean, you could simplify it some if you actually thought a version number, timestamp, those kinds of things can simplify this a little bit. Is this clear? This is called Gifford's quorum-based protocol. Okay, we will use this as the basis to think about things like consensus and Paxos in the next 2 or 3 classes. Okay, this is the most simplest way you are voting and getting agreement. Okay, servers have to agree on the contents of the file before they return the file. In this case, we said either it's a version number or all of the servers in the read quorum have to agree that the files match before you return to the server. This is the first time we've actually seen where there's voting and agreement before we return results. We will build on this when we talk about Paxos and draft and consensus, where we'll look at voting-based schemes and agreement in a lot more detail. Okay, so this is the first encounter where we have seen that. Any questions on this? All right. So here are some examples of what can happen in the quorum. So here we essentially have a coordinator is asking for file A. It's sending it to these 3 nodes. In this case, essentially you have 3 machines. They don't actually agree. Or in this case, you get all the versions. But let's say the read quorum is only 2. So 2 of them are actually agreeing. So you say the result is 2. Okay? So you don't actually have to ask all of the servers in this protocol. You ask all the servers and you find enough that have a read quorum to return the result. Okay? So you could have just ignored this, only send to 2 of the 3. But this is essentially doing the same thing. You essentially return the result of the majority, which is equal to a read quorum in this case. Okay? Here's yet another timing diagram. It's a little more complicated, but I can explain what is actually happening here. So you have essentially a chain saying change the value of A from 1 to 2. You return them to 3 of the replicas. Okay? You got 1 acknowledgement so far. And while this write is in progress, a read comes in. Okay? So this is concurrent reads and writes for a quorum. Okay? So the write is still in progress. Only 1 of the 3 replicas have actually said they have finished the write. So you ask for a file, A, you send that to all of them. You get the result. 2 of them have agreed to what it is. Okay? So that's the old result, not the new result. Okay? And you still return this. Okay? Because the write has not yet even finished. So you are still allowed to return the most recent version that the write quorum has is still the previous version. You're still allowed to return that. So this is a special case where there is a read that comes in while a write is in progress. Only some of the servers have seen it. In that case, you're still allowed to return an older version. Okay? Only once all of the quorum has completed the write, then this is disallowed. Then you have to return the next version. But while writes are in progress, the previous version that you agree on is still allowed. Okay, yes, question. Okay, question is why is it still allowed when it's older version? Because while a new write is in progress, the consistent version of the file you have is still the previous version because you have not yet finished the write. Okay? So that is the most consistent version. So you are allowed to return that. Okay? Once your write finishes, then you have to return the new one. So until a write has finished, the previous write is still the most recent write. Writes in progress are not the most recent write that are finished. So you are allowed to return the older version. Yes. Okay, question is this asynchronous replication, and do eventually all the servers get the write and so on, right? In the quorum-based protocol, okay, unlike the previous protocol where writes do propagate to all the servers, in quorum-based protocols, they don't have to. You just write to a write set. Those are the only machines that have seen the write. Okay? The reason we relax this is quorum-based protocols are also good at handling failures. Okay? Because if you did not do that, you waited for the write to finish at all the server. If one server goes down, write will block. Because I don't get an acknowledgement from that server. So if the write quorum is smaller than the full set, writes can still finish. You can still make progress in the system. Right? So let's say A went down, I can still perform the write on a write quorum of 10 because there's still 11 servers up, and that still works. Right? But if I made sure the writes have to go to all 12 servers, that's a problem because if a server is down, the write will not finish. So quorum-based protocol have a built-in property where some servers may be down and still system can make progress. Okay? In synchronous replication, you can't. In asynchronous, of course, you're not waiting for the write to even finish. But here we have that additional property. So, yeah, go ahead. Okay. The question is, does the quorum, is that decided at initialization or is it changing every time, right? All you're doing is you're setting the number of servers. So read quorum and write quorum is a number. Okay. So you set in that example, read quorum is 3 servers. Write quorum is 10 servers. You don't say which 3 or which 10. That the client picks at random. Okay. So if you're asking, does the client always write from C through L? That's not the case. You pick 10 servers at random, but you have to pick 10 because that number 10 is set. That is set at when the system boots up. You say, this is my write quorum size. That's the write quorum. Which servers to pick? That's up to each client. Each client can pick different servers that it wants. Okay. Okay, that's a good question. The question is, in this example, we saw that the write operation was done from C through L. Next time, if I make a write operation and it includes A and B, which now have an old version of the file, how is that going to work? Okay? In quorum-based protocol, when you update a file, you have to replace the file with the new version of the file. You don't modify a part of the file. It's not like you do an append operation where I just add one character to a file. Okay? If I did that, then of course A and B are stale. If I do another append, you will end up with some bad version of the file. So here, when we say write, you are going to essentially think of it as I just replace that entire file with a new version. So there is no making changes to parts of a file or something like that. That is the assumption. Otherwise, what you said will of course happen. Okay. Any other questions here? Okay. All right. So all good stuff. So let's think about a few other issues. Then we'll talk about fault tolerance as well today. Okay, so there are many other aspects of replica management which we will defer to the discussion on the World Wide Web because they make more sense in that context. So one is replica placement. In this, all of these abstract examples, we didn't actually ask the question, where are the replicas? Are they all together in the same data center? Are they geographically spread out? It actually matters. Okay? If you're geographically distributed replicas, synchronous replication will slow down. Okay? Because the propagation time to send the writes to all the server keeps going up as the server spread out more and more. Okay? In that case, asynchronous replication is much faster because you'll just write to the nearest copy and have that copy send things out in the background, but you lose some correctness guarantee. Okay? So you will have, in the case of the web, Okay? Replicas may be separated by continents. Okay? In file systems, if you do that, there is actually a big problem because you'll have performance. Okay? So where to place the replicas actually matters in terms of what kind of system it is. Is it the web? Is it a database? Is it a file system? We'll come back to some of this when we talk about the web, and we'll think about how to do geographic distributed replication, where to place the proxy. Okay, you can also cluster read requests based on where the proxies are. You don't have to send the write necessarily to other machines. You can send it to a local machine. All these optimizations will differ, not today. Okay? The second thing is are the replicas permanent? Are they temporary? In that we assumed in all of these examples, the number of replicas is actually fixed. Okay? That's not the case in many systems. The number of replicas by itself change over time based on the load. Okay? All kinds of web applications use dynamic replication. Okay? Not unlike a thread pool idea where the number of threads changes based on load. Think about the same thing for server, web server. The load goes up, where you have to increase the capacity, otherwise the servers get overloaded. Okay? So we'll scale up the capacity, the number of replicas will change over time. Okay? So how do you do consistency when the number of replicas is still not fixed? It's more complicated. We'll again come back to it at a later time. There's also whether some of this is initiated by the server, client, and so on. Okay? So these are all issues I just mentioned, but we will return to them. All we did today was to think about how to perform reads and writes in a consistent manner. Okay? We looked at replicated writes, local writes, those are all primary based. And then we saw leaderless protocols, which are agreement based. You ask multiple, you have them vote, and then they return the results of the vote. If the vote matches or the merchant matches, the vote succeeds and you're done. Otherwise, you repeat. So these are two classes of protocols. Some of this will come back. Okay? All right. So we talked about replication. We'll talk about and consistency. Caching is something we have not talked about. Okay? You are supposed to look at caching in your lab, lab 3, but we'll get to caching also when we talk about web. So hopefully all that would have been done before your lab is due. Okay? And we talked about many different consistency models last time, not today. Okay? Starting from strict consistency all the way to eventual consistency. When you put all of this together, you understand that replication consistency is a little bit a complicated topic. Okay? But what kind of consistency guarantees you provide actually matters in terms of the overhead you have, in terms of how you perform replication and so on. Okay? So I'll end not the class, but the topic here. Okay, we still have some slides to go. Okay, so we'll switch gears. I'll introduce the next topic, and then we'll continue that in next class where we get into more details. Okay, so this is a topic on fault tolerance. It's very intimately tied to replication. You can remember when I introduced replication a few classes ago, I said there are two reasons you create replicas. One is performance. Okay, you can essentially scale up when there are multiple copies. The other is fault tolerance. If some copies goes down, there's still a replica on some other machine, so you still have your data available or the machines are available. Okay? So now we'll get to the fault tolerance part of replication and look at what are some issues that we actually need to look at or some things like that. Okay? In single machine systems, okay, when faults occur, let's say the machine crashes, I think the system just stops. Okay? There's nothing really you can do other than restart the system. Okay? In distributed systems, when some components fail, we assume that if the system is well designed, the application as a whole continues to run. It's not going to stop. Okay? Other machines will take over the task of the failed nodes, or you just send requests to other replicas, so there's nothing to take over. There are already replicas, so other machines take on the load and so on. Okay? So distributed system, partial failures are possible, but we can still make the system continue to run. Okay? Now, why is it that you want to implement this in this type of fault tolerance or replication in larger system? This is because even if failures are independent, okay, the probability that there is some component has failed in the system essentially is going to keep going up as the number of components in the system increases. Okay? The reason is the probability of a single component failing is P. Okay? Probability that there is any failure in the system is 1 minus P to the power n. Yes, P to the n is all of them failed, 1 minus P to the n, there is some failure. Okay? Now, as n goes to infinity, P to the n term is going to go to 0. Because P is always less than. Okay? So the probability of failure will tend to 1 as n goes up. Okay? A simple math explanation, but what this actually means is any large systems, okay, failure is actually the common case. Some components being down is the common case. It's not an uncommon. In small systems, failures are the rare case. Something goes down, something bad has happened or unexpected has happened. But you take large system, 10,000 machines, 100,000 machines, some fraction of the nodes are always down for any reason. Okay? So if you don't build these large systems with fault tolerance in mind, the system will fundamentally not work because the math will work against you. Okay? Because that's how the probability of any failure in the system is going to be very high. So you want to ensure that all large systems have fault tolerance techniques built in so that the system can continue to work, because failure goes from being uncommon to being very common in larger systems. Okay? With that in mind, let's look at how we design systems and why that's really not the right way to design larger distributed systems. Okay? So unlike many other kinds of things you can design, okay, computing systems are not designed to be very reliable because software fundamentally has bugs in it. Okay? And there's no system where you wait for every bug to be resolved before you actually send the product out and people start using it. Right? So there's always bugs even in production software, which means that you can have crashes or something incorrect happens because the software is buggy and so on. Okay? For a long time, that's everybody accepted that as the way software systems were. If machine hung, you just restart the machine or you reboot, maybe things work and so on. Okay? But now, okay, this model is actually not the right one because computing has actually become very common, and this goes a lot beyond having just computing devices like laptops and desktop. Your TV has a computer in it, your car has a computer in it. Almost any device that is smart in some way has a built-in computer. Okay? And you don't want to export this model of how we have used computing system to the entire world, saying TV fails and reboot the TV. Okay? Your car doesn't start, reboot the car. That kind of stuff people are not used to. Okay? You might have been used to that, saying, okay, your laptop hangs, maybe I'll restart it. But as other people who are not tech savvy are not used to this model. Okay? They expect things to work. You put on a light, if you say that you have to restart the light bulb because it has some computing element in it, that doesn't quite work because people expect things to just work. Okay? Especially things they don't think of as computing devices. Okay? So in some sense, as computing has not just become more distributed, but more ubiquitous, okay, we need to make them more reliable, because otherwise we depend on these other systems. We add a computing to it, computing element to it, and it becomes unreliable. Doesn't quite work. The world actually still wants most of its things to be reliable. Okay? And now everything is computing driven. We want to increase reliability. So in some sense, we want to build our systems to be more dependable, not just distributed system, any kind of system. Okay? So what are the requirements for dependability? There are 3 metrics I'll talk about. Okay? First is called availability. Okay? What does availability mean? Availability simply means the system should be available to use at any given instant. Okay? At any given time t, what is the probability that the system is actually running, up and running? Okay? That's called an availability metric. It's usually measured in terms of a percentage. That's the percentage of the time the system is up. Okay? And usually you will see in industry terms, you will basically be given availability metrics in some number of nines. Okay? That says what essentially you want at least 99% reliability. That's called 2 nines of reliability. If you have 99.999% reliability, that's called 5 nines of reliability, because there are 5 nines in there. Okay? So you have 2 nines, 3 nines, 4 nines, and 5 nines. 5 nines is basically some of the most reliable systems you can get. Even 5 nines means you can be down for 6 minutes a year. Okay? So you can think of those are the most reliable ones that you can buy, because nothing is perfect. Okay? So that's basically 5 nines is what you can get in most cases. Most systems don't even get to this. If they get to 99%, you are in good shape. Okay? 99% means you'll have several hours or maybe up to a day of downtime every year. Okay? And you can keep reducing it until you get to 5 nines of reliability. So if you think about, this is how you will see industry systems actually marketing their availability, saying this system has so many nines of reliability. Anything below nines, if you're 95% and so on, that's not considered good in terms of being a dependable system. That's its availability, but not a system that you boast about saying this is a good highly reliable system. Okay, so you have to at least start with 2 nines for anyone to even consider a system being good. Okay, 5 nines is great, but not very many systems get there. Okay, so that's availability. Reliability simply means that the system should run continuously without failure. It is reliable, it doesn't fail. Okay? It's of course tied to availability, because if you're less reliable, your availability will go down. Okay? And safety essentially means that if there are some failures in the system, they don't translate to what are called catastrophic failures. Okay? If some components of the node goes down, the whole network should not come down. Okay? That's essentially safety property. Okay? And this, of course, lots of big systems still have this problem. Okay? You will see all kinds of problems where you make a small change in the cloud platform, the entire cloud goes down, right? So like lots of users are affected. Okay? And then you saw not too long ago, AT&T was trying to upgrade its network. It made one small change to one cell tower, whole network went down. Right? So that's not the kind of system that you want to have, where you make one change or one thing fails, the whole thing system goes down with it. Okay? And of course, when you have mission critical systems, that's really bad. And so you don't want this to happen in an airplane or a nuclear reactor, where one thing component fails and the system essentially goes down. And that's going to impact people's lives and so on. So when lives depend on it, you really want your system to be safe and reliable and so on. Okay? So that's your safety property. Maintainability simply says that if a system has failed, it should be easy to recover and repair. That you need to be able to bring it back up. Because no matter what you do, something might go wrong and the system might fail. The faster you can bring it back up, the more maintainable it is. Okay? So these are all properties you want in your system for dependability. Okay? We are not going to specifically look at each of these metrics, but we look at this concept in general, saying what can we do to try to get a lot of these properties into our systems. Okay, any questions on this? All right. So we'll talk a little bit about different kinds of fault, and I'll end the lecture today by showing you one way by which we can implement a very simple fault tolerant system, okay, using replication. But before we get there, let's try to think about what kinds of failures or faults can occur. And we will classify them in terms of 3 different faults. And there's a 4th one I'll get to later next class. Okay? Transient fault means essentially it's a one-time fault. Something goes wrong and then it comes back up. Okay? So it's transient, it never returns again. Okay? Intermittent fault means it's a fault that seems to keep occurring every once in a while. It randomly appears and it disappears, then it appears again and so on. Okay? There's something wrong, but maybe the system is failing, but the component stops working temporarily, it works again, and then it fails again and so on. Okay? And permanent fault means some component has permanently failed. It's not working anymore. Okay? So you can have different kinds of failures. Okay? The transient failure is a one time. Okay? There's a bit flip in the memory or something like that. It causes some error, but it's a one-time thing. There's nothing wrong in the system. It's a transient error, causes some issue, but it's gone. There's nothing you can do about it. Intermittent means it's kind of component that maybe works, doesn't work, and things like that. Permanent is gone down. Okay? With that background, let's now think about all the failures that these kinds of faults can cause. Okay? So we'll talk about a bunch of them. So the crash failure, okay, simplest type of failure. Machine is down, it just crashed, doesn't work. Okay, that's our crash failure. Omission failure says that the server is not responding to incoming requests. Okay, so you can have 2 types of omission failure, where it's not responding because it does not receive the request, or it doesn't send a reply. It gets the request but doesn't send the reply, or basically it doesn't receive the request. In this case, there's some issue where the requests coming into the network are not getting to the server. Okay? Crash failure means OS has crashed. Here there's some network issue. Timing failure says that the server is responding, but it's taking a really long time. The time it takes to respond is beyond the tolerance that you have said is adequate for the system to be performing well. Okay? Maybe it takes 1 minute for it to return a web page. Most users will not wait for a minute after they click on a link. After 10, 20 seconds, they'll say something is wrong and move on. Okay? So that's basically, and then there are other kinds of systems, like if you have audio and video streaming, you need data to be coming in at a regular interval. Otherwise, there's a timing error and your video will freeze or something like that will happen. So all kinds of issues. In this case, it's not that the system has gone down or there's any failure. It is just slow. And it's so slow that it's basically beyond the tolerance that where users find it acceptable. Okay? That's a timing failure. Okay? You can have response failure, which means that the response is incorrect. I get a response, but it's giving something that's incorrect. Okay? And there's arbitrary failure, also called Byzantine failure, which says the server can do arbitrary things at arbitrary times. Sometimes it may not respond to requests. Sometimes it will give the right response. Sometimes it might actually give garbage response. The server is basically, it's almost like the server got hacked and the malicious hacker is doing arbitrary things, so you cannot trust the server, whatever it is. So that's a Byzantine fault or an arbitrary. Okay, that's the hardest type to look at. So we'll only look at two types of faults in today's class and next class. Crash failures, which are the simplest. Server crashed, there's no response. It's not that it's giving wrong response. When it works, it gives the right response. When it fails, it produces no response. Very simple. Okay, that's the first type. Second type we'll look at are arbitrary responses where the server may choose to do anything. We just don't know what it's doing. It may give bad responses, no responses, right responses. So we can't trust the server. Okay? How do you detect these faults? How do you recover from them? These are the ones we'll look at. The middle ones we'll just ignore because you can translate some of them to one of these two categories. Okay, is that clear? All right. So with that, today I'm going to end with this slide, which is to show you a system with 3 components and show you how we can implement a very simple fault tolerance technique that only deals with crash faults. Okay. All right. So this is the non-replicated version. Okay, you have components A, B, and C. Okay. What these components are doesn't matter. This could be components of a hardware circuit. This could be components of a multi-tier application. Doesn't really matter. All we know is input comes to A processes it, sends something to B processes it, sends something to C produces the output. Okay. This is the non-replicated version. So clearly, if A crashes, B crashes, or C crashes, there's going to be no output. Okay, only dealing with crash failures. Okay. So what are we going to do? We'll replicate all of them. Okay. So we'll say I'll replicate A 3 times, A1, A2, A3. I'm going to essentially put a voter that says, send me your output. I will take the majority and I will pass it on. Okay. So I can handle one fault. Okay. So if the A1 does not respond, that's fine. If A1 gives me the bad response, that's also fine. So in this case, I can also deal with an arbitrary fault where it's basically producing something that's incorrect. Okay. Because the voter is taking the majority. Okay. And the 2 of the 3 are working right. 2 of them will agree and the 1 will disagree. But I can still vote. I can take the majority response and pass it to the next stage. Okay. So I put a voter between these 2. Okay. But you will see that the voter is also replicated. Why is that? Okay, because I said you have to replicate the component and then I have to vote on the majority. Okay. And then I take the majority vote of A1, A2, A3, which is the replicated version of A, and then pass it on. Okay. But if you just did that, you put one voter in here, okay, you can ask what happens if the voter fails. You can't have any single point of failure. There's no guarantee that the voter will work, but the component A fails. Maybe it's a web server, maybe it's a circuit. So the voters also have to be replicated, which is why you see there are 3 voters, just as there are 3 of these. Okay? So the way this is done, this is called triple modular redundancy. There's 3 of everything. Okay? So you will take A1, A2, A3. Okay? You will give them to each of the voters. Okay? Each voter will take the majority vote and pass it to the next component. Okay? So even if the voter fails, but the components are right, the other 2 voters work. So the B1 and B2 and B3 in this case will get the right response. So everything will be fine from the following stage. Okay? So you can't assume that you can only replicate some component, not any component, because if there's a failure, any component can fail. So essentially, you put the simple idea is you replicate each component, you put a voter, but the voter stage also has to be replicated. If you do this, then you can tolerate one failure in the system, and then things should be fine. Any component can fail, and everything is just going to work as is. Okay? In this case, you can also tolerate multiple failures, but only of specific component. You can't have a component and one of its voter fail at the same time. That actually doesn't work in some cases. But you can have A1 fail and some C1 fail, and then still things still work. So there's some redundancy, but you cannot guarantee that if two components fail, things always work. If certain components fail, you can make things work, but generally one component fail, any one component will always work. Okay. Now, if you look at this, you will see that fault tolerance, the only thing I want to end with this, fault tolerance is coming at a price. Okay. We have tripled the price of our system. 3 times the hardware, 3 times the software you got to deploy to get this property. Okay. That's a high price to pay. You want just to make your system fault tolerant. Because I mean 3 times the price, because if I have to spend X, I'm spending 3X just to make sure nothing fails in the system. Okay? So in many cases, not users, but application designers are not really willing to put in such a high investment on fault tolerance. So they may not actually give you this high level of guarantee. But if you want good guarantees, you have to really pay a high price for fault tolerance. This question. Yeah. So, okay. Question is, can you not send to have some replicated servers where you, or some standby servers where you can do it? There are all kinds of techniques. Okay. There's always a trade-off between how seamless is it? Is there any downtime? Do I need to do recovery? In this case, there is nothing to recover. Everything just continues to work as is, but the price you pay is very high. Okay? And here we assume that you can make arbitrary output and still work. If it was crash failures, you don't need such a high tolerance. Because crash failure says either you work or you are down. I just need 2, right? Because I'll just say, I just put 2 because if one fails, it's just not going to produce bad results. Stops responding. I can take the other output and pass it along. I am good. Is that clear, what I just said? But if you have arbitrary failures where I can produce garbage, I need to have other nodes that outward the bad node. So you know that that node is bad, it gets outwarded and you pass the correct result. So when you have arbitrary failure, the cost is high. For crash failures, you double the number of servers, because for every server you need a replica that works. For arbitrary failures, which actually you are going to have 4 components, because for every component here, you have 3 plus you have all these extra voters. Yes, question. Yep. The question is, I said that as you have more components, the probability of a failure goes up, but we are also adding more components to make it fault tolerant. So does that actually defeat the purpose of replication to begin with? So if you don't have enough replication, of course, things will fail and nothing will work in the system if something goes down. So you have to have replication. But the general idea is what I meant there was, if you have lots of servers, let's say there are not 3, but maybe n stages where n is very large. Okay? That is when the probability goes up. Now, you go from that to essentially 3n. Okay? That does not increase the probability that much. So n is what is essentially causing the probability to go up. The fact that you add a constant term, multiplicative term doesn't significantly increase it. It will increase it. There is no question. But there is n that is actually matters, the number of components in the system, not the degree of replication. So we are talking about degree of replication is 3. N is the number of components in this chain. Okay? N is more important than D, which is the degree of replication. In this case, they both happen to be 3. Okay? So they wash out one another. But in general, N is going to be much larger than the degree of replication of any one component. Okay? Any other question? What if the voters don't have agreement? Is that your question? Okay. So our question is, what if the voters don't have agreement? In this scenario that we mentioned, where at most one node can fail and produce bad results, the voters will always have agreement. Because if you look at any one voter, what is it doing? Taking the input from all A1, A2, A3 and saying, what's the majority? Okay. Each of them, you see that there are 3 lines going into each voter. They're basically taking the input from A1, A2, A3. Now, we are guaranteed that if only one of these can fail, then there's going to be agreement. If 2 fail, there is no agreement. But we are not saying you can tolerate 2 failures. Okay? This system can tolerate 1 failure. If there are 2 failures, the system doesn't work. You need higher levels of redundancy. So there's 2 concurrent failures. This system can handle 1 concurrent failure one failure, not concurrent, one failure. And if there's only one failure, the voters will always agree because the other two are assumed to be right. And they'll produce the right response and they outward the wrong node. Okay, so that is not a problem. But yes, if two of the three fail, if A2 and A3 fail, okay, you can't have A1 actually dominate because they might decide they will agree and send a bad result out. Then all bets are off, right? So that then nothing works. So this will tolerate one failure. So yes. Okay. Is there any formula to decide how much, what's the max you can tolerate for such system? There's a formula. I will talk about it, I think, next time. Okay, and I'll explain to you what you have to do is you have to first decide how many failures you want to tolerate. And the formula tells you how many replicas you need to have. Okay, so for crash failures, it's I think 2f plus 1. For other things, it's higher. Okay, that clear? Any other? Sorry, it's f plus 1, not 2f plus 1. But if you have one failure, you need two nodes. If you want two failures, you need three nodes. So you always need one node that's up. So it's basically the number of failures plus 1 is what you need for crash failure. For Byzantine failures is actually higher. It's 3f plus 1, but we'll get to that next time. Okay. All right. We'll end it here today. For those of you who came late, I reminded people that Friday is Monday's schedule. Okay, there is a class this Friday, which is on university schedule, so don't forget. Okay, we'll have a lecture as per our Monday schedule on this Friday. Next Monday is, of course, a holiday for Patriots Day. Right? Let's stop here. We'll continue.